Hello and welcome back to KivyTips. I believe you have met with a C extension in Python, and if not, then you just haven't noticed it yet. C extensions are awesome things that can speed up your code, but that's not all. C extensions can also use a third-party library and make its functionality available in Python. This is what we'll look at today. Specifically, we'll look at how to wrap a C library with Cython and how to later use it in Python. Wrapping with Cython, however, isn't the only thing you need to understand when you want to use the library, because stuff can go wrong pretty quickly. That's why I'll show you how such a C library can be created, what's necessary for compilers to produce dynamic link library, or DLL, or shared object SO, or static libraries, and how to make such a library available in a C extension produced by Cython. I'll have a file with simplified instructions linked in the description and even directly in the repository, so you can have them like some kind of cheat sheet if you want. Also note that the instructions for GCC on Windows are meant to create a DLL, so if you are going to use GCC in there, it might be good to switch to appropriate names. There will be 3 steps: writing a C library and compiling it to something more usable, either a DLL on Windows or shared object on Linux. Step 2. Testing the library with a simple C program. Obviously, you don't want to try wrapping a broken library. Step 3. Writing a C/Cython extension that uses the library. Mostly you don't want to write the Python C extension from scratch, it just takes a lot more time than learning Cython, and you will need to know where to find what. With such cases, you might as well just switch to the C itself without interactions with the interpreter. Step 1 is mostly done by someone else, and you just want to use the library. But we look into how the process goes to see what files are necessary when using it with Cython, and to get a basic idea what's necessary to do when, for example, the library maintainer doesn't provide binaries for you, or what actually to look for when you find a bunch of DLLs or SOs without the necessary stuff. A little disclaimer: in this video I don't care about optimization, compiler tricks, or whatever. It's just a simple tutorial to show you how to wrap without pulling your hair out. For more info, find a book about C and read your compiler's manual. As you can see, we started with a simple C function that just returns a string for us. We make a simple header with declaration of this function, and that probably could be it if you would want to make only a static library. We use extra and C to mimic libraries that support both C and C++. Then we need to make it available to the compiler and linker so that it knows what symbols to kind of make public to anything using it. Static libraries can introduce a lot of problems with licensing, so we make our custom library able to create even DLL or SO. On Windows you can achieve it with a special export, but we need to include even the calling convention for it. You can find links in the description and in the instructions. With GCC, however, you don't need to add the calling convention, but there still need to be some kind of exporting for the symbols. I use macros to be able to change specific methods just with a compiler flag. Obviously, the keywords aren't there just for fun. We need to add it to our declaration so that we can make our hello function visible. Let's test our library now. We make a simple C program that uses our hello function. You can see that for the compilation, we will need the library header, which has the declaration. Let's look how to compile the library now. First, I'll start with GCC and compile the C file together with setting include and library path to the current folder explicitly. This gives us an object file. We then take the object file and create a static library with an archiving program. Good, we have a static library. Let's use it to compile the simple C program. We need the header and the library file which is currently named hellolib.a, and we say to GCC to compile it. The lowercase l isn't a standard syntax, because all of libs on non-Windows systems tend to start with lib prefix. The colon, however, allows us to give the full name of the library so that the linker can find it. The all flag shows warnings if something goes wrong. Now we have the testing program compiled. Let's run it. Seems fine. Let's move the static library somewhere else. Still runs just fine. That's because the code from the library is copied to the executable. Now let's look at creating a shared library. We tell GCC to pass some arguments to the linker so that the library identifies itself like hellolib.so.1. Again, why it's like that is both in the description and in the instructions file. It's important mainly on Linux. So we finally have a shared library. Let's compile our C program and use the shared library instead of the static one. The static library is currently in the GCC static folder, which the compiler doesn't see automatically, and that's good. Again, set include and library paths to the current folder and link against the shared library now. It compiled fine, let's test it. Program works just fine. After moving the shared library somewhere else, where the program doesn't see it automatically, makes it crash. You can see a lovely pop-up error, and the amazing program is not responding. Sadly, you won't get much out of this pop-up, but that's for some other topic. Well, we know how a program behaves with a shared library. Let's look now at the Microsoft compiler. I use the C++ build tools, so I don't have everything thrown at my system path, but that's just fine when you know what to look for. This particular batch file makes the compiler available from the console. Compile the library again, just with a little bit different syntax, and from the object file create a library. Static one for now. Now compile the testing program and don't forget to link against the library. Again, we need the headers and the library file, which now ends with .lib. After execution, the program runs just fine. When we move the static library away, it behaves as expected. Shared library is created a little bit differently because I decided to trigger creating a DLL only when some variable is defined. We use a flag for the compiler to define this variable at the beginning, set it to create a DLL with LD flag, and set the include path to the current folder. There is a difference between GCC and this compiler because we use the library path later with the linker. We have DLL created. Let's use it in a program. Link against the .lib file and set the library path to the current folder. Compile just fine. The program works, and when we move the DLL, it again behaves as expected without the lovely pop-ups telling us that DLL is missing. The first step is done. This is when most of the people that wrap the library actually start. They have the library files available, no matter static or dynamic, and they also have the headers. Let's switch to Cython now and create an extension we will be able to use in Python with an ordinary import. We started pulling the symbols we want to use from the header. It's more or less like Python's import statement if you just need to roughly imagine what does it do. After that, we can access the hello function, but for now we can use it only in the particular file. We create a Python function now where we wrap the C function for two cases. One is just plain return of the output we get from the function, the other is creating a C variable in there to store the output and return it later. As you can see, this is how you can create a C variable in a Cython file. This simple line that creates a C variable is pretty much what of Cython tutorials or talks are only about. Imagine I add there a squared function instead, time it at the end to compare it with a squared function written in Python, and here you go a Cython tutorial. Unfortunately, there's way less tutorials about wrapping libraries and the advanced stuff you can actually do with Cython. Of course, it's mostly written in the Cython documentation, but come on, it's not the shortest one, and the videos or talks can give you some hints here and there instead of wondering what did the author mean by that part. Anyway, we import the Cython file, which at the end will become an extension, and we just use the Python functions we created. Those are the ones that start with def, not cdef. Create a HTML file at the end so that if we do something more with Cython, it shows us what can we speed up by converting the code to C with cdef functions or variables. As we work with the compiler and linking against our library when creating a simple C program, this hasn't disappeared. It will be there and will haunt you until you learn it properly. So we can make it either automatic or we can use console arguments. I use the second option because it's a safer bet with all those Cygwin and other tools that can tell your script that you are on a completely different platform, though you are not at all. We use the same syntax as we used when compiling and linking manually. The dash and lowercase l with some characters after it. Beware though, because the row to Microsoft's compiler is long and during the row a .lib suffix is appended automatically. Therefore, if you add it here as hellolib.lib string, it will not see your library because of a different name. then we need to get our current folder, and the safest way is probably through using the setup file itself and pulling the path from it with functions. Then we name the package. It's the name, which would be the package installed with pip. Create a base for setup function and let's tell it what our extension is and what to do with it. We need to name the extension. It's the same thing we try to import in the main.py file, and it's the name of the final file. Therefore, if we would install this particular package with pip, we might need to change the Python import to cython_hellolib.cython_hellolib, and maybe even add an empty init.py file to the package. Again, a different topic, and we want just to wrap the library and run it in Python. We set the sources, include folders, library folders, and the libraries we want to link our Cython file against. There is also a possibility to change language to C++. So, this is pretty much the setup file. Let's compile now. First, we do static linking. The Python program works just fine after we remove the library, as it just copied it into the extension. When we tried the dynamic linking, we can see it works just like a simple C program from the beginning. We proceed with another compiler and with Python too. Good, that's the Windows. I use the same instructions, all except the define current directory command, and went through the same steps quicker now on Linux Mint distro. Everything worked just fine. Notice the small change, however, with an argument you have to use before running a program that uses a shared library. That's because on Linux the system expects you to set path either to program or to the library during the packaging, so that it can safely find its desired library and, for example, doesn't collide with the rest of them. So, that's all for now. I hope this video will help you with the first steps. If you get more familiar with it, feel free to make contributions, for example to Kiwi repository, which also uses this way of wrapping libraries. You can find more resources, links, and useful stuff in the description and in the instructions for this video in my repository. Thanks for watching.